Today we're going to expand on what we talked about yesterday with exponential growth and decay. When we had a growth and decay model yesterday, we were given a time, how much money is going to be in your bank account after so many years. Well, today what we're going to do is we're going to give you the amount in your bank account, and we're going to say, how long will it take? So now we're looking for the time, where before we were looking for our y. Okay, so to do this, you do need your graphing calculator, so if you could take that out. How we would do that is, remember when you are graphing, you always have a y1. So we have y1, and that would be 2,000. And the other side of your equation is y2. So y2 is your 800 in this problem, times 1.3 raised to the x power. Okay, what we're going to do is we're going to put this into our y equals on our calculator. So go ahead and hit y equals, and we would type 2,000, and then we would type 800 times 1.3 raised to the x power. What we're going to see is our graph is either going to be going up if it is growth, or down if the graph is decay. In this one, we know it's growth because it's greater than 1 inside the parentheses. But our screen starts, or we need to figure out where it is at 2,000. So if we were to hit graph, oops, if it will let me. Okay, if we were to hit graph, this is our normal screen, which is a 10 by 10. And we don't see anything show up. Okay, so in order to do this, we have to set our window. So if you hit the window key, this changes what you see on your screen. Since we're talking about growth or decay, we're only going to be looking in the first quadrant. So our x min and our y min will be 0. So if you want to change those. Our x max, if you see right here, should be 10 or 20. I like to leave it a little bit higher, so I'm going to put this to 20. And then our y max, which is how far we're going to go up on the screen, needs to be just a little bigger than the biggest number in your problem. So in this case, our problem, the biggest number in our problem is 2,000. So we're going to do 2,100. And again, you can pick any number you want as long as it's bigger than 2,000. Now if you hit graph, this is what you should see. The blue line represents whatever we're talking about at 2,000. And the red line represents the exponential growth of that problem. So what we're looking for is how long it took for this growth to get to 2,000. So if you remember, we would hit second trace 5, enter, enter, enter. So whatever this is, we're going to round to the nearest hundredth, so it's 3.49. So our answer would be 3.49 units. Okay? And it also says to sketch your graph, so it looked something like that, and put a little dot on your intersection point. So that's what we're going to be doing today. So problem number 2 says you deposit $800 in an account that pays 6% interest compounded yearly. This is an exponential growth problem. So when we write our equation, we would say y equals 800. Since it's growth, it would be 1 plus our interest, which is 0.06 raised to the t power. Yesterday, we substituted this into t, but that's not what we're looking for. We're looking for how long it's going to take for our account, excuse me, with $800 in it, to get to 1,200. So this value here goes into y. So it's 1,200 equals 800, 1 plus 0.06 to the x power. X and t are the exact same thing. So again, we have a y1 and a y2. Your y1 is 1,200. Your y2 is 800 times 1 plus 0.06 to the x power. So when we go to our graph, we're going to clear what we had. y1 is 1200, y2 is 800 times 1 plus 0.06 raised to the x power. If you hit graph, if you notice, our screen is big enough for us to see that intersection point. So let's graph that intersection. So it looks like this. Okay. And then we need to find the intersection. So second trace 5, 1, 2, 3. Enter 3 times. So it will take 6.96 years for your bank account starting at 800 to reach 1200. The question though is, how long will it take to reach 5,000? So really we're just changing our y1 because your equation y2 stays the exact same. So when we go to our graph, our calculators, we would hit y equals, only change y1 to 5,000 because this still has not changed. We're still looking about the same thing. If you hit graph, notice you're only seeing your exponential growth graph. We're not seeing that blue line that shows 5,000. If this happens, remember you go to your window and change your y max to a little bit bigger than your largest number. Well, in this case, we have 5,000, so let's say 5,100. And there it appears. But look what happens. Our red line now doesn't intersect. So we have to go back to window and change our x max. Let's change it to 50. And there we go. Now we can see it. So if we were to sketch our graph, it would look like this. And then we need to find the intersection point. So second trace 5, enter, enter, enter. So in order for your bank account to reach $5,000, it has to sit for 31.45 years. Crazy to think about. The next problem. A newly hatched channel catfish typically weighs about 0.3 grams. During the first 6 weeks of its life, growth increases by 10% each week. So this is a growth model because it's getting bigger. So we would say y equals 0.03, because that's the beginning weight, times 1 plus 0.10, because it's growing 10%, raised to the t power. Part B is just like what we did yesterday. Find out how much the catfish weighs at the end of 6 weeks. Okay, so that's our time. T equals 6. So because we have a t, we can just substitute that in to our calculator. So we don't need to graph this first one. We just say 0.3 times 1 plus 0.10 raised to the 6th power, because we were given our time. So after 6 weeks, this new catfish weighs 0.53 grams, right? Because it starts off in grams, it has to stay in grams. But part C says, how long will it take for the catfish's weight to double? If it doubles, that means it has to reach 0.06, or 0.6, sorry. So that's the original weight, 0.3, doubled to 0.6. So since we are looking for the outcome and how long it took to get here, then we have to set it equal to our original formula. So here's your y1, here's your y2. So if we go back to our graph, clear everything, you have our y1, which is 0.6, our y2, which is 0.3 times 1 plus 0.1 raised to the x power. If you were to hit graph, it's set for 5,000, and this is really close to 0, so we really don't see any change. So let's change our window. Let's change our X max back to 20. And let's change our Y max to 1. Because if we're looking for 0.6, we only need to go to 1. So now it looks a lot better. So let's find that intersection point. Zoom trace, second trace 5. Enter, enter, enter. So it's going to take 7.27 weeks for that catfish to reach 0.6. And again, our graph looked like so. One more problem, and that says our summer youth camp had a declining enrollment from 2001 to 2014. The enrollment in 2001 was 320 people. Each year for the next 10 years, the enrollment declined, that's a key word, by 2.1%. Let t equal 0 represent the year 2001. So since it's declining, this is a decay problem. So we would say y equals our original enrollment times 1 minus 0.021. That's the 2.1% raised to the t power. Okay, so how many people are there in the camp in 2010? Well, if t equals 0 is 2001, t is going to equal 9 in 2010. So we would substitute that in, y equals 320, 1 minus 0.021 to the 9th power. So if you did this, 320 times 1 minus, because it's decay, 0.021 raised to the 9th power, it's going to give you, it'll let me, 264.36. But since we're talking about people, there's 264 people at the camp in 2010. How long will it take for our enrollment to be 301? So since that was what we were looking for originally, we need to find the time for this. So 1 minus 0.021 to the x or t. This is your y1. This is your y2. So when you go to your calculator, I'm going to clear this, go to y equals, you would say 301 is what we're looking for, so that's y1. And then our equation, which was 320, 1 minus 0.021 raised to the x power. We're going to change our window, because right now our y max is at 1. So let's change it to, let's say, again, it doesn't matter, we'll say 340. And then hit graph. Notice on this graph, it's not going up like the others. It's going down because this is a decay problem. So if we find that intersection point, it would say 2.88. So 2.88 years. And again, it wants you to sketch the graph, so it's going down on this one. Okay? If I want to know how long it takes for 250, all we have to do in this problem is change our y1, because the equation does not change. So erase your 301 and type 250, and then hit graph. And again, it just moved this blue line down a little bit, so we need to find our intersection, which is 11.63. And that's years. So it would take for the enrollment to get to 250 people, 11.63 years. All right, enjoy the video. Goodbye.